Welcome to our talk on ready-to-use virtual machine pool cache using warm cache. Yeah, next slide, please. Okay. Before we get into talk, I would like to give some of the background on what eBay is. Like Dr. David mentioned, like online commerce has drastically changed, and eBay being one of the oldest online retailer. We have presence in more than 33 countries. We have around 171 active million buyers, which I think should have drastically increased now. We have more than 23 billion GMV as of Q1 2018, and more than half of it comes from mobile sales. Our eBay app has been downloaded more than 400 million times. Next slide, please. So we have been hiring during these times, and we have been hiring across all major cities in all the countries. And I think because of the coronavirus, there is a lot of potential for remote work, and we are hiring in almost all the domains, right from management to recent college graduates to research scientists and engineering and data science. So you could explore pop up on Google. Yeah, next slide. Okay, with that, I would like to hand over to Sudeep. He's going to continue with the rest of the presentation.
Thanks, Deepak. I'm trying to outline here what's the problem statement that we've been trying to address. The conventional on-demand virtual machine provisioning methods on a cloud platform can be really time-consuming, and they are typically error-prone, especially when we need to provision large quantities of VM in large numbers, right? In quick numbers. So let's consider an example like a company like eBay. So eBay has our own managed clouds that we host in different data centers. Typically, they vary in sizes. They can be on with a smaller footprint to a medium footprint. Unlike Amazon, our footprint is much more smaller, as we only look for our own internal solutions to be hosted there. So what we typically try to do, at least on these managed platforms, is to spawn different kind of applications. Now the applications can be either stateful or stateless depending on what they do. Applications like databases needs to be stateful, and if you have multiple replicas of a database, you need to be careful where you place a replica. You ideally don't want to place a replica on the same host, because if that host goes away, you essentially lose a replica, and potentially losing the data itself. So and this is a typical problem that we've been having within our managed cloud platform. What are the different to just double click on the why aspect of what we are doing it. So the capacity or the amount of resources that we have on our managed platforms, our managed cloud offering is quite limited, right? As I said, it can be on with different footprints, and multiple tenants share the same infrastructure. So the capacity is really limited, and when you have a limited capacity and you want to be really infrastructure or infrastructure aware, it becomes a much more difficult challenge. As a stateful application, my desire would be to place different instances of my VMs on a different rack based on what they do. And I should be also be mindful of the transient delays or delays in the network, the disk failures that could actually increase the time to provision VM instances. And this is very true. Like, for example, if we have a downtime because of my database is not scaling up, I'll have to quickly provision, say, 10 more instances of the of my replica, which can of my database, which can take a read traffic. So what is the solution that we came up with? We actually created a warm cache module, which actually creates a pool of VM instances well ahead of the actual provisioning needs. And this particular module is typically or is rule based, and based on different capacity that gets added to the infrastructure, we create different rules, and based on that, it just creates it over a period of time. And the advantage of having these pre-baked VM instances are they're already ready to go. So it allows us to quickly provision. This cache is continuously built over a period of time. So it can actually, based on the infrastructure, as the capacity is added, it will actually slowly take down a VM node if it sees too many VMs are provisioned on a host, and then try to provision it on a separate host or a separate rack. The nodes are also periodically pulled for the health status, and unhealthy nodes are auto purged from the active cache. And this we need to ensure, because we need to make sure that whatever instances are loaded on the cache are healthy and ready to go. We also have interfaces which allows us to tune how the warm cache is built over time, and to take remediation actions if need be, to influence how the cache is built. Oops. So let's look at, I'm trying to present here what's a typical hardware that eBay uses and many other companies use, right? You generally have one single rack, and within a rack, you would have multiple fault domains. Ideally, in our case, we have like 2 fault domains. And within a fault domain, you will have different VMs of different sizes based on what the customer had asked for. Now, all these VMs are typically hosted on a hypervisor. So the difference, if you have a rack with 2 fault domains, ideally what it means is that the rack as such is on a one data center, but each of the fault domain would be mutually exclusive in the way how the power is given to these fault domains, and the disk isolation and everything else is isolated. So they're kind of mutually exclusive, but within the same data center. Wherein you have can have multiple VMs provisioned on top of it. Um, Now, this is a multi-tenant system, right? So you don't have ownership of all the VMs that gets hosted on a hypervisor or a fault domain. Yeah, one team, multiple teams can share this. Um, based, like, given the, and this was an important exercise for us to do to actually understand the infrastructure to come up with this kind of solution. So as part of that, what we did is that we decided, we knew that there are different kinds of VM sizes that are required. So based on those size rules, we spawn these instances, and as the instances are spawned, we collect the information on the hypervisor ID, rack ID, the server ID, and OS scheduler hint is something that we use when we actually have to create a batch of VMs, so that they try to at least spawn them on different hypervisors and the created time, right? We store this information. So as a provisioning request comes to the cache, we use this information to make sure that we based on the user input, we actually give them the VMs from the cache. So the way it works is that we have a leader elect model. Before that, I'll just briefly touch upon what all the different components that depend on this cache, and which is outlined in the paper. We use console, which is like a metadata store for us, which says, which we use console for storing the information on what all instances were created on which data center. We also use console for service discovery. Apart from that, console is also used for leader elect, which I'll just walk over in a while. We also have something called a configuration management system. So as different VMs are created, we actually we store that information idly in a we model that as a topology on a configuration management system. And as the VMs are taken out and used it for needs like, for example, provisioning Elasticsearch, then we model that onto CMS as well. For actual provisioning, we use OpenStack. We are moving towards Kubernetes. So as part of OpenStack, we use the Nova APIs to actually spawn C3 instances. On top of the cache, we have extensive monitoring and logging that we have built. The monitoring is based on Elasticsearch. notifications are periodically sent from the module, which depends on the cache, which looks at the different health of the VM instances and the distribution of the VM instances on the infrastructure. And these are typically sent either by a Slack webhook or by email notification. The actual flavor info that the hardware is actually stored onto Mongo service. So as a capacity team adds a new infrastructure, if they add a new infrastructure, those infrastructure rules are actually captured onto Mongo. So we briefly touched upon console being used as leader elect, and that leader is responsible for building the cache over a period of time. The way it works is that there will be multiple leaders that work at any point in time, and they will never overlap with each other. And console leader log helps us to do that. When a leader is selected, we read this metadata from console and we start preparing the cache, and leader is completely responsible for doing this. And it will not build all the VM caches, so you can say 100 VMs at a time or 50 VMs at a time. Based on that, it will prepare the cache, persist the cache info, and relinquish the reader log. At some point in time, some other leader node which is also participating leader election can become a leader and then go ahead and create those rules over a period of time. So from the user perspective, this is typically what happens. Say I'm a SaaS provider of say Elasticsearch, and I want to get VM instances. So I use the get VM instances from the cache. It presents itself with a lock on the console and gets a list of VM available. Now when the request user had made the request, he would actually make the request in typically 3 ways. He would say either I want to be completely rack aware. That means that when if I'm asking for 5 instances, all 5 instances should go on a different rack. The best mode, best effort mode, wherein you'll try to get VMs on different racks. If not, you'll try to get them on different hypervisors. And if not, then whatever is available, you give it back. And then there is a hypervisor aware mode, wherein you're actually essentially trying to get it on different hypervisors, which is typically useful if your application have high network IO throughput or the disk IO throughput, because each hypervisor has its own networking card and a dedicated disk. The cache, as I said, like it looks up into the list of available VMs that is present at that point in time. It gets those VMs, releases the log, and gives back the control back to the user. Now, once that is done, it is responsibility of the user to actually use the VM and provision whatever needs to be provisioned. We also periodically look whether that VM that we released is something they have used. Because if no applications are hosted within a period of say pre-configured period time interval, say 1 week or 2 weeks, then we actually go ahead and delete the VM and try to get a new VM which gets added to the cache subscript. So we briefly talked about different provisioning rules. This slide tries to capture that. In the rule, you can see in the rule below, we have something called max instance per cycle, which essentially says that how many instances you want to spawn in a cycle, how many minimum fault domains you need, and if you really look at G2 HIMEM 16 SLC 16 is like a flavor on our infrastructure. It could vary for different companies, but this is a flavor that we have. And we apart from that, we can as you actually do the actual provisioning use request, you can also have a user data field, which basically is a script, typically a bash script, which is like a base 64 encoded. So as a VM is provisioned, if you want to load up something, it could be for your own VM monitoring, or if you want to spawn some daemon jobs there, for example, if you want to ensure that the server is sending some logs to a certain endpoint, you can configure all that through a user data script. So in this rule, you are basically saying that you want to provision 12 instances of this particular flavor, and the leader, when it tries to provision, it would try to do 5 at a time. and you need at least a minimum fault domain of 2. We have a lot of dashboards that we actually built, but I think it's not very clear. But just to give a kiss of this one, this is a data center dashboard. So the big blue bubble that you see in the center represents a data center. On that data center, the next ring on the concentric circle represents the different kinds of racks that we have. So that gives a rack distribution, and on top of the next concentric circle would give you the different kind of hypervisors that we have. On those hypervisors is the actual VMs that get provisioned. So typically this gives a representation of where the total skew is. We also also capture details on how many instances are there for a particular flavor, like total count of 74 present on the data center, and these are the different types of flavor that is present. This gives a quick snapshot into someone to see what is a capacity that is present on the warm cache available for provisioning. And if you think there is a certain flavor that is lacking in capacity, you can add that rule, or you can also take down VMs from a particular rack which you think is over provisioned, like you don't want to really have a lot of ready to go VMs there. So to try, I'm trying to summarize here. So basically the idea is what we wanted to do is to have an ability to quickly flex up. With this module, what we have been able to do for one of our internal solutions that we call as Elasticsearch as a service, we actually can provision huge clusters, like 100 node clusters within a matter of few seconds, and that has really helped us in terms of our own RTB. And the idea is that since this cache is built over time, we can be good at being infrastructure aware, and the VMs are already loaded into cache, so there is very less errors in terms of actual provisioning requests for the VM. We based on the whatever we have built out of the warm cache, we can also do better capacity planning. What we are looking at is since we have multiple different kind of managed cloud offerings now within eBay, Kubernetes being one of them, we are trying to migrate the same thing onto Kubernetes as well. And the teams here has like really benefited a lot from going this route. Um, yeah, thank you.